going well. We have a few clicker questions. I like those because it gives me feedback and we can actually discuss things that arise from those clicker questions in class. There are some questions on the answer that I don't know the answer to, so you guys should help people out. It's actually really useful as a student to get known as someone who's proactive in help. If you want to ask someone for letters of reference to get a job or get into grad school, being known as someone who's proactive in helping other people is really good for you. So if you see questions on the Calvin site like, does this particular package of Python work, and you know the answer, but I have no idea what the answer is, you should answer it. Okay, so just please, let's start off this everyone trying to help each other answer questions and do things. There's a help for Python on Windows now posted. Any other questions about that? There's another Python tutorial. I know lots of people went yesterday. It was useful. Right. A few nods. Good. So it's only really that code now that we need to be able to run. And please install Python 3. Okay, does anyone have any questions about anything before we start? So what we've done last time was we talked about searching. We had the idea of this model of a graph in terms of nodes and arcs. And a state space graph is the nodes are states and the arcs are actions. Later on we look at other actions, other types of graphs. But just at the moment we're looking at graphs where the nodes are the states of the world and arcs are going to be actions. And what we really need in a state is enough information to answer this question, is it a goal state? And what's the next state given an action? And that's going to be a neighbor of that in the graph. Does that make sense? Any questions about that? All right, so let's start off with a clicker question. Remember, it's A, B, A. All right, next. What's the definition of balanced rationality? A, actions that lead to a random state. B, making decisions that are limited to one's own ability and resources. C, forming plans based on one's past experiences to reach a goal. Or D, making decisions without considering one's own perception, knowledge, and time. Worrying about your own limitations. So not, some of the ones we're going to look at today are going to be essentially perfect rationality. Any questions about that one? Next one. Which of the following is needed for state space assumption to work? A, the agent randomly chooses the possible next action. B, the agent's actions are deterministic. C, there's only one goal state max. Or D, an agent's actions are stochastic. All right. Everyone said B. Turns out there's no right answer to this question. They're all wrong. So even when we do, later on when we're going to do actions where we're unsure about, there's still an underlying notion of a state that we're going to use. So when people build agents to reinforcement learning, for example, there's still an underlying notion of a state about what's true in the world. We might not know it. We typically go to work out. We have uncertainty about what's the state, but there's still an underlying notion of a state. Okay, so this notion of a state doesn't rely on the fact that it's deterministic. It's just the assumptions that we're doing now are deterministic. So So even when we get stochastic actions, there's still a notion of the state that we're going to use. Okay, it's just basically what's true about the world, and we're just going to know what's true, but we're still going to have a notion of the state. I thought it was a bit unfair if I asked none of the above, because that would be, people wouldn't expect you to know that answer. Okay, just another. So state needs to contain enough information to A, predict everything possible about what's true, just determine the effect of an action, C, just determine if an agent has achieved its goal, D, determine if the agent has achieved its goal and determine the effect of an action, or, The state's always obvious in the problem, isn't it? Yeah? So all you need to do is work out whether you can achieve the goal and what the effect of the action is. Other things that are irrelevant to that can be left out of the state. So if it doesn't tell you what you're going to do with your action, it doesn't tell you whether you've reached your goal, it's irrelevant, you can forget that information. So that's all the state needs to do. And I'm glad no one said E, because designing the state is actually usually not obvious for the problem. Any questions about that? And another one from the posting on the answer. What's it between an arc and an edge? So arcs are directed edges, right? Closely you said that. Yeah, the arcs we're defining here are directed. B is just wrong. C might be true. Depends what you mean by that. But edges are often used to change it. Any questions about that? So today we're going to look at two different search methods. We're going to look at depth-first search and breadth-first searches. They're actually very dull methods, but a lot of the other methods we're going to do are built on top of these methods. So it's good to understand how they work. So we're going to demonstrate how depth-first search will work on a graph, look at how breadth-first search will work, and we also want to look at the space and time requirements for these different searches. So what we did before was we had this idea of graph searching. This is what we did the last time. Given a graph, start nodes, goal nodes, we implement this explore paths in the start node. We maintain this what's called this frontier, and as search proceeds, we're going to expand the frontier. Okay, so we have all these explore nodes. We have a frontier of paths from the start node and then we have the unexplored nodes, and now we're going to try to expand the frontier in order to incorporate that. So a simple idea. So here's a pseudocode to this. Where you input a graph, you input a set of start nodes. So the graph just consists of essentially the nodes and the arcs, a set of start nodes, and there's a Boolean procedure goal, which tests if n is a goal node. So we've got a procedure that tests whether something is a goal node. We have explicit start nodes. We're going to start off, initially the frontier is just a set of paths of length 0 that just contain start nodes. And then we're going to just repeatedly loop while there's still stuff in the frontier, we're going to select and remove a path from the frontier. If the end of the path is a goal, we're going to return that path. And otherwise, we're going to look at the neighbours of the end of the path, and we're going to add those neighbours to the end of the path and continue. Does that make sense? Sort of obvious what's going on? Any questions? So if you look at the so here is the Python definition. So this is the same one that was in your code before, except I stripped out these displays because displays are used for tracing it. And the idea is that this is supposed to be exactly the same as what that pseudocode is. That's why we chose Python in here. While the frontier is not empty, we're going to pop a path from the frontier. If the end of the path is a goal, we're going to return the path. Otherwise, we're going to get the neighbours from the end of the path. And for every arc in the neighbour, we're going to add a new path. Okay, so this is supposed to be just like the pseudocode. Okay, so we're just going to loop here. We're just going to keep repeating until while the frontier is empty, and we're going to keep popping elements from it. Okay, does that make sense? Should be reasonably straightforward, and it has this nice property that we can keep re-asking for questions. So if I create one searcher, the searcher up here, all the searcher does is creates the problem, and it creates an empty frontier, and then adds all the start nodes to the frontier. So just what we did before. And it has this nice property that we can actually create a search and just ask for the first path and ask for the next path. We can just start from the previous time when the searcher ended. Okay, does that make sense? So let's have a look at how this works. All right. So which value is selected from the frontier defines the search strategy. So in here, when we say select and remove a path from the frontier, we can select and remove any of them. Which one we choose defines the search strategy. So we're going to find a number of different search strategies, and all we're going to do is just change which element we're going to select. Okay, that's all we're going to do in there. The neighbours of a node define a graph. The only information we need from a node is what are its neighbours. So this neighbours defines the graph. Right, so if you look at there, the only property we need of NK is whether there's a neighbour, and this goal predicate defines what a solution is. So if we're going to change the graph or change the solution, you're just going to change the goal predicate, and we continue from the search. Okay. Any questions so far? The first search method we're going to do is depth first search, which treats the frontier as a stack. Do you remember what a stack is? Who remembers what a stack is? Who doesn't remember what a stack is? All right, good. So a stack always selects one of the last elements out of the frontier. So this list of paths on the frontier is this P1 to PK. If P1 selected is the first element of the frontier, then we're going to then we can add them to the front of the stack. So when we remove them, we can add it to the front. And P2 is only selected when we've explored all the paths from P1. So if you look at this graph, it's always going to search this the same way. Here we're going to assume that we're going from left to right. So we're always going to choose the leftmost one before the rightmost one in these examples. So in here we always go, we have the stack initially contains just the node marked 1. It initially contains the node marked 1. Then it contains 2 and something else, which I'll num, which is this thing. And then we're going to move 2 and we're going to add 3, 4 and this thing. And then we're going to choose 3 and add its neighbours onto it, which are 4 and 12. We're going to go 4 and 12. Whoops. And add 2, 3, 4. 2 is 13. Thank you. 4 and 12. And 13 and this one. And it's going to keep going down like this. It's going to do 4, 5. When it's explored 6, it has no neighbours, so it's going to go back and look at the neighbour of the second neighbour of 4, which is the 7. It's sort of, we often call this backtrack. We go down, explore this, and we backtrack up to find 4, then there's 7, and we're going to explore 8, 9, 10, 11. And once we get to this 16, the grey nodes are all the elements on the frontier. So once we've expanded 16, we have the elements that are on the frontier are the greyed out nodes there. Okay, so they're the first 16 nodes. And at this stage here, we've expanded 16. The frontier is essentially children of 16 plus all of the sort of aunt or uncle nodes in this. If you think of this as a way of having parents and children, it's the aunts or uncles who are on the stack. Okay, does that make sense? And let's look at the So let's look at what happens within this graph here. This is our graph that we're going to keep comparing things to. This is depth first search. So what we're going to do is we're going to select a node. So initially, so what happens here, O1, O3 is our start node, R1, 2, 3 is our goal node. We're going to select the first start node. We're going to add its neighbours to the frontier. It has 3 neighbours, TS, B3, and O1, O9, and now we have a new frontier. We're going to select another node here. It's going to select one plus, one down. It's going to select TS. Now that's the path that's found to TS. We're going to add its neighbours to the node, which is male, and then we have a new frontier that is this male B3 and O1, O9. Okay. What node's going to get selected next? Male, right? The male is the last one added, so it's going to get selected next. The male is selected, we're going to add its neighbours to the node, there isn't any. So the frontier ends up being just B3 and O1, O9. These both added at the same time, so it depends on which order we're going to put those in the stack. So let's assume it's B3, so we're going to select B3, add its neighbours to the node, and we have a new frontier. So either B1 or B4, the last one's added, and we can keep going. So we're going to choose B1, we're going to add its neighbours, so there's C3 and B2. We're now going to choose one of those, add that to have a new frontier. We're going to select that, the top element of the frontier, we're going to add its neighbours. We're going to have a new frontier, we're going to select one that was on the path. We select the new neighbours, we're going to add its neighbours to the node, we have a new frontier. And how many paths are on the frontier now? Who's been keeping track? Ooh. 4 or 5. Anyway, there are 5 paths on the node because there are 2 different C3. There's 2 different paths to C3. Sorry, there are 5 different paths on the frontier. So there's two different paths to C3. There's one via C1 and there's one directly from C2. So which one's going to get selected first, those two paths? Which one's going to get selected next? Yeah, the C1 to C3, because that was the last one added. All right, we select the C1 to C3. We can add C3's neighbours to the node. Right, we can have any neighbours. Then we're going to have a new frontier. It's a bug in this program. We can add any, we can set, that should have been green. Right. We're now going to have a new, select the C3, have a new C3, have a new path to C3. It's the second time we've chosen C3. We're now going to add its neighbours to the node, to the frontier. Now for a new frontier. Yes. What happens if you have a cycle in the graph? What happens if you have a cycle in the graph? What does it do? Yeah, it goes round, keep going round and round the loop. Okay, so if you have a cycle, it's going to keep choosing it over and over again. Can anyone guess which path it's going to find to the goal now? I keep stepping through this. Which path it's going to find? So far at this stage, we're selecting this node. Which path is it going to find? Yeah.
We go O1, 103 up to B1, B2, then B4, 109, 119, 123, R123.
Right, it's going to go the one that goes via this red one, then starts going down and up. That's the path it's going to find, because that's the path it explored first. Okay, let's step through this quicker. We're going to select O109, we have O109, we've added its neighbours to the node. We have a new frontier. We're going to add its neighbours to the node. Now we have a new frontier. Now we're going to select our O125. Notice what's happening. R123 is a goal node, but it's on the frontier. We haven't checked it yet. Right? We're now checking O125. We're going to add its neighbours to the node. We're going to add its neighbours. Sorry, we're going to add its neighbours to the frontier. And now we're going to add its neighbours. Now we have a new frontier. Now we're going to select R123. Now it can stop. Does that make sense? It's going to be important later on that we only check for goals after it's been selected for the frontier. Okay. Questions? I click OK.
So how many times did the C3 check up this track? How many times? Twice or just once?
C3 is affected twice. There's two different paths. The way to think about it, the frontier contains paths. Because there are two different paths to C3, it's going to be selected twice. Okay? Yes?
Couldn't you optimize that out? Couldn't you optimize that out?
Yeah, we're going to optimize it. We're going to optimize it. But it's not obvious because it's going to be space-time trade-offs. So it's not going to be obvious how to optimize it. If I keep stepping, this is the frontier. We're going to just keep going. We're going to check what the next one in there. We're going to check storage. It has no neighbours. Then we're going to go way back to B to right to O103. I forgot that path was still there. Eventually we're going to go back and select this other one from the very early on. We're going to explore paths from it. Okay, any questions? People think they understand how this works? All right, let's do a quiz. Which shaded goal? The shaded goals, we've got the shaded nodes, the goal nodes. Which one is Jeff first search going to find, given the goes choosing leftmost one first?
That was easy. Brent, that was like
Which one's he going to find first? Good. Everyone understands? Good. Perfect.
everyone understands.
Do any of the 6 people who didn't get this have a question? All right. So, does depth first search guarantee to find the path with the fewest arcs? No. Right. So it doesn't guarantee to find the path with the fewest arcs. What happens if infinite graphs or graphs with cycles, if there's a solution? It's guaranteed to find the solution. No, right? It's not guaranteed to find a solution. You can go wandering off in cycles. What's the time complexity of the function of the length of path selected? Oh, do you remember the time complexity? Maybe n squared. Oh. Yeah, he's right. There's no upper bound. Right, because if you have a path, if you have a path here and you probably explore all of this, there can be an arbitrary amount of time spent in here before you get to this node. So the answer to this question is there's no upper bound on the amount of time you can do this. Right, there's infinite complexity. There's no upper bound on how long it can take. What's the space complexity as a function of the length of the path selected? How much space do we have to store? What do we have to store? Remember what we were storing in this? Way down here we have to store effectively these things. How long is this? How much space do you have to store? It's a function of this. There is an upper bound. It's n, right? So the number of nodes is n times the number of neighbors a node can have. Yes?
If that's a function of path velocity, there, again, same issue, have potentially infinite number of other paths, so you have to store on this path.
No. No. You're only storing this one path. Once you've explored this, you're here, you've thrown this away. You're not, that's not, there's only one element on your stack here. Sorry? So the space complexity is the path length n. And is n times the maximum number number of
Stop watching.
neighbors.
Just stop watching my thesis.
Neighbors. That's the maximum size of the frontier. Yes.
So the, this is number of, for, is on the number of neighbors, right, so the,
Well, if this is unbounded, then this is unbounded. Yeah, so if this is bounded, then this is bounded. But typically in these graphs, we don't have infinitely many neighbors. So most of the complexity we're going to do is going to have a bounded number of neighbors.
Why do we have maximum instead of average?
Oh, because you might, everything down this path might be really bad, even though the average over all of the graphs might be small. We might have happened to choose down here the bad cases, number of neighbors. So there's sort of 2 to the n possible paths in the graph of big Ben, and not all of them are going to be average. Some of them are going to be extremely bad. That's why the space complexity is like this. Questions? How does the goal affect the search? Do we head towards, yeah?
If you have multiple goals, then you might want to find like the focus on one of the goals.
If this doesn't affect search,
Which one do you like better for search than?
well, maybe. The answer is that it doesn't. The only way it affects the search is when it stumbles upon a goal, right? It just keeps searching essentially independently of the goal. The goal doesn't affect where it's searching until it gets to, doesn't affect where it's going to until it stumbles on a goal. Okay, so it's going to search effectively the same space independently where the goal is. Will this be useful for Google Maps? Right, we want to get from the start node to the goal node. You want to search the space of things which are independent of the goal? No. But the basis further up. All right. The next one, breadth first search is going to treat the frontier as a cube. It's always going to select one of the earliest elements added to the frontier. So I've listed the path as P1 to P. When P1 is selected, then its neighbours are added to the end on the right-hand side. And after P1 is selected, P2 is selected. We're just going to cycle through them. Okay? So if you look at this same graph that we did before, we're going to order this graph. We're going to first choose 1, then 2, and we're going to always choose the oldest neighbour on the oldest element of the frontier, which is 4, then 5, then 6, and it's going to 8, 9, 10. It's going to what's called breadth first search. It just goes across the breadth of this graph. And after we've done 16 nodes, the orange nodes here are the nodes that are on the frontier. Any questions about that? So let's go through this one. Let's reset the search to the breadth first search. And we're going to choose a node, choose the neighbours, have a new frontier, we're going to choose a node. We can add its neighbours on, we have a new frontier. So which node are we going to choose next? B3, right? We choose B3 next and add its neighbours. Then we've got a new frontier, it's going to choose the oldest one, which is the oldest one. 0109. And add its neighbours. Then it's going to choose the oldest one, which is male. Right, we choose that. and its neighbours. Rather than you can choose the oldest one, choose B3, B1 and its neighbours. It's going to go to B4. It's going to choose 0109 and its neighbours. Oh, choose 01. Oh. Yeah, so we're doing everything now 2 steps away from it. So first we did everything 1 step away from the start node, then everything 2, and everything 3. So now it's exploring everything 2 steps from the neighbours. Now it's going to, this also is 2 steps and its neighbours. Everything 3 steps now, next will time, next loop through. Okay? Keep doing this to do everything 3 steps. We'll finally get something that's going to do everything 4 steps away. Make sense? Okay. Any questions about that? You understand this? All right. Just make sure everyone knows what's happening. Which shaded goals will Brett first search? It's the same question as last time. It's exactly the same graph. That's the same graph. A, B, C, D, or E. Which node, which path to which node will it choose first? Oh no! Started. Gosh,
You said it.
I just started. All right. That's where we'll go now. I think that's it. It's not good. All right. C. Good. Almost master. All right. Any questions about that? Anyone who answered A or B want to ask why? Any questions about that? We're going to just go through across the. Remember, we added the front, left, to the right. All right, that's the same questions again. Does Brad first search guarantee to find a path with fewer stars? That should be a path, does it? Yes? No? Yes, right. It's going to find the path with fewer stars. So the answer is yes. It should say a path with fewer stars. The typo on the start. What happens on infinite graphs or graphs with cycles if there's a solution? Does it act like breadth, does it act like depth first search? What happens in this case? You go into an infinite loop. Who thinks it goes into an infinite loop?
I think there is no solution.
Hmm?
There is no solution.
Sorry?
Oh, there is a solution.
There is a solution, and there's no one has infinitely many neighbors. So hang on, who thinks it goes into an infinite? Can go into an infinite loop? Who thinks it doesn't go into an infinite loop? Who doesn't think? Yeah, it doesn't go. It always finds it, right? It's always going to hold. What's the time complexity is a function of the length of the path selected. What's the time complexity? times max neighbours. All right, that's right. Then squared times max neighbours. Max neighbours. What else might it be? The function, this is breadth first search. Where n is the path length. And this is time. Yeah.
Exponential?
Okay, it's exponential. Since it's exponential, does anyone know what you know what it is? You say what's the exponent of the base?
Max neighbors?
Max neighbors to the end. Okay. Any other hypotheses? Each time here it can keep exploding. The max neighbors is 3, and each time through the branch it can triple. Right, each time it can triple. So this is the time complexity. Questions about that? What's the space complexity function of the length of the path selected? How much space does it use? What's on the frontier? Storing the frontier. The only thing that's how big is the frontier? That's the only thing we're storing. Remember? How big can the frontier be? Same as this. Right? Both time and space are exponential, in particular there, max neighbors to the power of n. And again, how does the goal affect the search? Well, it wanders around till it gets the goal, right? It doesn't, just when the goals are not affecting the search. All right. Any questions about that? So it turns out Google Maps doesn't use breadth first search either. But because it's effectively because of the space, depth first search is used a lot because of the space. Breadth first search is hardly ever used because of the space consideration. Unless you're a very small finite graph, then you can do breadth first search. But in lots of these cases, Google Maps is not going to use it, it uses too much space. Also, we do one more algorithm, and we'll stop. So sometimes there are costs associated with an arc, and the cost of a path is the sum of the cost of the arcs. Right, so the cost of this path n0, n1 to nk is summing over all of the arc costs. We're going to sum up all of the arc costs from n0 to n1, n1 to n2. The obvious thing, right? If you have a whole lot of line segments in the graph, it's the total time. A whole lot of distances they add up. An optimal solution is the one with the minimum cost. And there's an algorithm called lowest cost first, like breadth first search, except we're always going to select the path to the frontier with the lowest cost. Instead of choosing the oldest one, we're always going to choose the smallest one. And the frontier is a priority queue ordered by path cost now. So the first path to a goal is which? Which path does it find first? the lowest cost path, right? It always finds the lowest cost path first. Just like breadth first search always found the fewest arcs, this always finds the least cost path for goal. Will the arc cost 3? What is it the same as? Breadth first search. Right? It has all of the same problems as breadth first search, as exponential time, but used for finding shortest path. Any questions about the, all right, let's, any questions? I could go through and get, I think it was talked about. I was going to put it back on the, wait a minute, I'll go through this again. Oh, no, it's not. So far we've seen 3 strategies: depth first, breadth first, and lowest cost first search. So depth first always selects the last node added to the frontier, breadth first the first node added to the frontier, and lowest cost first produces the minimal cost of the path. So which are complete, guaranteed to find a solution if there is one, even on infinite graphs. Which one's complete?
Breadth first will be complete, and lowest cost one would be when you have zero cost paths.
Yeah. Okay. What about halts? What about space? What do we do with space? What about the paths of finite graphs? There's no solution. Is it halt with loops? They halt. They're guaranteed to halt. And finite graphs, even if they have cycles, it's going to go on forever.
Breadth and lowest cost will always depth control.
What if there's no goal? Yeah, what if there are no goals?
There are no goals, why would you say search algorithm?
Well, the goal might be disconnected. You might want to find a road to somewhere on the Sunshine Coast, right? I don't think there are any roads to element. The goal might be disconnected from where you're going. No, fine. So none of them are guaranteed to hold. If their goal is disconnected from where you are, right, where you want to find a road from here to Pender Harbour, there isn't one.